Hi everyone, today we are working with our new skill called finding volume. That's a crazy volume by perpendicular cross sections. And as you guys saw in just a little bit ago when I demonstrated on our calculus in motion, the idea is that we're taking a 2D shape and we're going to grow this 2D shape into a 3D shape. So let's take a shape like this here, right? And we're going to, this is, let's say, X and Y. And we're going to grow Z from it. Let's make Z go this way. And we're going to grow out Z from it. Right, so if you guys aren't good at 3D drawings, I don't know. So our first example, let's do something easy called squares. So we're going to grow squares from this. And let's draw a couple squares here. Let's see if I get my brain right. I haven't done this in a little bit. So we're going to draw little squares. Yeah, let's probably a little bit like that. Okay, so we're going to draw squares, and as the height gets bigger, so is our square. Right. So I just draw one shape. You don't have to draw a bunch of these. I just draw it once because we have to just get an idea of like where our parts are from. Now, how do we find the area of a square? The area of a square is s squared. Is that okay? We call it s squared, referring to the side. And in this case, the side is equal to our equation. Let's say this is, let's see, what should we call this? Y is equal to negative x.
Mr. Cole,
Yep.
what did I say above area? Did it say square?
Squares.
All right.
Mm-hmm. We'll call it x squared minus 4 negative. Put a 0. Let's do a positive here. No. Well, let's give us our right equation here. I'm just trying to think. 2 negative x squared. I was just trying to make this up, but man, this is not a good idea. X minus 4, right? Those are our factors. And we want this to be facing down, negative. That's going to be a plus over here. 2. This is 4. I'm just trying to make this up quickly. And me making it quickly means me doing it slowly. Good job, Mr. Go. And negative x squared plus 4x. There you go, 4x. There you go. Okay. So that's our upper equation. Negative x squared plus 4x. Our limit on the bottom is just y is equal to 0. So how would we find this area? Area is just s squared, so we describe this as my s. Right, that's my side. And to find the area of a side is we just square it. S in this case is negative x squared plus 4 minus 0. You guys okay? This is my upper minus lower. Because that's the length of this side here. That's this length here. And isn't a square s times s? Because they're both the same size. So as s on the base increases, so does s as the height of my square increases. So as we talked about integrals add up stuff. So what are we trying to add? We're adding slivers of squares. And the way we add make this into volume, we do integral from 0 to 4 of our area times little dx. It does not give us our volume. A little sliver of dx, so area times a little bit of width. I would call this like a width. That gives us volume. How do you find the area in this shape? This shape is a square, so it's really 0 to 4 of s squared dx. What is your s in this case? 0 to 4 of negative x squared plus 4 squared dx. All right, so is that hard? No, not for a square. Okay, not for a square. What if I make this into a rectangle? Rectangles, we know rectangles are not balanced, right? One side is longer than the other. So I have to give you a characteristic. Let's say, find the area, same idea. We'll draw a little parabola here going. So this is the y is equal to negative x squared plus 4x. And what if I ask you to do perpendicular cross sections? Oops, I misspelled that one. Cross sections are rectangles, where the height is double the base. Okay, the height is double the base. So if I'm drawing my 3D drawing here, oops, the height is double, oops, okay, the height is double the base. So if this is S, this is 2S. So I just drew it one sheet so you guys can see that this is a rectangle, and as the side increases, the distance of my base increases, so does the so does the object get bigger. So what we're doing, we're adding slices, right? So this is 0 to 4, same equation, 0 to 4, of our area times a little bit of dx. Give it with some thickness. But what's the area of this rectangle? What's the area of this shape? Isn't this shape S times 2S? That's the area. Simplifying that, this is just 2S squared. So the cool thing is that when I rewrite this 0 to 4 of 2S squared dx, since the 2 is a constant, that just kick that out. Guess what? It's going to be the same equation. So we're going to notice something about all these equations, is that they're all going to be s squared with a modifier in the front. Because I'm going to show you our next one here. What if we were dealing with a semicircle? And the reason why we're saying semicircle, because that gives us a dome. We can do a full circle. Let's do the same graph here. Okay, so I'm going to draw a dome here. Okay, and as you can see, this dome is a semicircle that is perpendicular, sticking out of this graph. Okay. So what's the area of this dome? So we're looking at a semicircle as my cross section. Okay, we're still looking at volume, so this is integral from 0 to 4 of area times a little bit of dx to give us a little bit of width. What's the area of a semicircle? Well, the area of a circle is that pi r squared. But we're going to divide this by 2 because we want half a circle here, semicircle. Now, we have to be careful here because this is the one that's one of the trickiest. And maybe some of you guys fall in the camp of diameter people. But if you look at that, that is not the radius, is it? That's the diameter. So for us to be able to change it into r, so we can say, call this s. Let's call this s again. So isn't r equal to s over 2? Help me out here. Does this kind of make sense? r, the radius, is, if I call this full length like we've been doing so far, that's an s, the side. To get the radius, it's just half of that. So I'm going to do my conversions right now. S is equal to, r is equal to s over 2. Well, perfect, because I can write this equation as an s equation. Pi over 2 s over 2 squared. Take a look here, because that is just another way of saying radius in this problem. If we simplify, it'll be pi over 2 s squared over 4, which becomes pi over 8 s squared. Take a look at that, folks. Our area is defined by the side squared by a modifier of pi over 8. Let's plug into the equation. Integral from 0 to 4 of pi over 8 s squared dx. Pi over 8, would you guys agree with me that pi over 8 is just a constant? We can kick it out. This is pi over 8 integral from 0 to 4 of s squared dx. And guess what? Remember, we already found out what s squared is. All right, what if I wanted a circle? A full circle, full circle. So I'm going to draw this again. Oh my gosh, drawing this so many times. And then if I just drew a circle's going to be a little bit weird. Okay? You guys get the idea. Half of it's on top, half of it's on bottom, okay? The s value is right in the middle of the circle. Okay, so integral from 0 to 4 of area dx. What type of area? We're dealing with a full circle here. Area is pi r squared. Great. But the problem is r is not s. So r is s over 2. Because again, the radius is half the side s, which is the length of the top to bottom. If you forgot, s in this case was y, was our equation, x negative x squared minus 4x minus 0, right? That's upper minus lower. Okay, so if we just plug it, we just rewrite this in terms of s, pi s over 2 squared, which is pi s squared over 4, which is pi over 4s squared. Rewriting this, integral 0 to 4 pi over 4 s squared dx. Does anyone have an idea what I'm going to do next with this pi over 4? Right, I'm going to probably kick it out, right? Pi over 4 integral from 0 to 4 of s squared dx. Looks a little familiar to you guys? Do you see a pattern that's probably going to be emerging here? The pattern is we're always going to be using s squared in these types of problems, but the constant in the front is going to change the shape of it, because all these are still going to use s, because that's what we have, upper minus lower, just the modifier in the front. Let's go ahead and change our equation. Let's take a look at one. What if we want to use equilateral triangles? Equilateral triangles. And no joke, they'll tell you, build this shape with equilateral triangles. All right, let's build the shape. If you build it, they will come. Here is my parabola again. You guys must be tired of this parabola. If I was using a different program, I could probably just cut and paste that. If I was using the nicer programs, like Notability or something. Okay, so let's draw a equilateral triangle. I'm going to draw my S shape here. Here's S. And we'll draw a triangle. We'll try to make it look kind of a little bit off to the side. Oops, sorry. Right, so that's my equilateral triangle. Now, do you know the area of an equilateral triangle? Because it's the integral from 0 to 4 of area dx, right? And we have to somehow find that area. What is the area of an equilateral triangle? Now, I'm going to tell you guys what the area of a triangle is. Area of a triangle, remember, is 1/2 base times height. Okay? And in this case, an equilateral triangle, let me draw you an equilateral triangle here. Equilateral triangle, I'm going to call the base S, right? That's the S sitting on this flat part here. We know equilateral triangles is 60, 60, 60, right? And if we want to cut this in half, all this fancy stuff, this is 1 over 2S, right? And since it's a 3690 triangle now, we know this is S over here. Yeah, right? S, 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 because it's all equilateral. And I'm not sure if you guys remember this, but this is going to be the square root of 3 over 2S. Square root of 3 over 2S. And I'm pretty sure you guys all memorized that, right? Of course. So to find the area of this triangle, 1/2, base, which is S, the full base is S. The height is square root of 3 over 2S. Right? 1/2 base times height, which is square root of 3 over 4 S squared. All right. How do you guys like that? So if we know the area of this triangle, let's write the area is square root of 3 over 4 S squared. See how we use S as my side because that's the full length from top to bottom. That's our upper minus lower, our easiest value to find. Okay, the area, the volume would be integral from 0 to 4, square root of 3 over 4 S squared. Okay, and then we're going to say what else? Dx. Right, because we got to make this a little volume, and we're left with square root of 3 over 4 integral from 0 to 4 S squared dx. Okay. Let's keep on going, right? What if now we end up with a different type of triangle? There are a couple of triangles that we're working with here. Next one is an isosceles. Let's actually just do, isosceles. Right triangle. Okay, and we're gonna pin this versus a isosceles. Darn it, I spelled that one. Isosceles right triangle. Now, I just wrote the same thing twice. And the reason why is we're going to use the same shape twice. Except, can you guys think of an isosceles right triangle? It looks like half a square. Half a square. Now, are all the sides of this triangle the same? Okay, let me draw this out. If I draw an isosceles right triangle, we have these sides are the same, right? And then we have a right angle, leaving my angles 45 and 45. So you would agree that the legs are the same, but the hypotenuse is different. And just as a reminder, the hypotenuse is going to be, if you guys remember your 30, 60, 90s and 45, 45 triangles, this will be x square root of 2. Just to talk about it, okay? Just as a reminder, okay? Now, if we build our two different models here, let's go ahead and draw our two little shapes here, and you tell me, are they going to look the same or not? Okay. Oh, that's a little crooked, whatever. So I'm going to draw my little parabola again. Hi, parabola. Long time no see. Right? So on the left, let's make the leg on base. Okay, the leg, these are legs, right? These are legs. We'll put the leg on the base. And this one over here, we'll put the hypotenuse on the base. So if I put the leg on the base, I'm going to try to draw this as best as I can. Go out and then come down like that. And then form a right triangle. Nah, that looks terrible. Let me go the other way. If the vertex goes out this way, it'll come out this way, and I think it's harder for you guys to see this way. Let's go the other way. Let's make this stand out like this. I think that looks better. All right, can you guys see that this is my leg? So it's standing straight up, right, and then sloping back down. Okay, and if you flip it the other way and have that side stand up, it's the same thing, right? Okay, that's the leg on base, and I'm gonna call this again that leg, and that's gonna be S. Versus falling flat on your face, and everyone watching you. That's my right angle, and this is my leg on. This is my hypotenuse on the base. So as you can see, depending on what part of the triangle, it changes the shape. What about our last triangle, Mr. Ko? What if I start rotating this guy? Aren't they all the same size? Aren't they all SSS? So no matter how you rotate it, it doesn't matter. Because they're all the same S, right? Because it's the equilateral triangle. But when it comes to isosceles triangles, they don't fit right anymore. So if it's on the leg or the hypotenuse, it changes our equation. Now, can I give you some hints here? Well, let's draw it this way. Sometimes it might be easier for you guys to just draw the shape out the cross section. If I call this S, and that's a right angle, and this is 45, we know the other sides are S, S, and S squared of 2. Whoops, yeah, S squared of 2. But to find the area of a triangle, please remember, it's just 1/2 base times height. You guys agree with that? 1/2 base times height? And in this case, it's 1/2 S times S, which is 1/2 S squared. Now, I'm going to throw a little secret there. Have we seen S squared before? What shape was S squared originally? Wasn't S squared originally just a square? Can I show you the hint for this one? The trick here is also, if you don't want to memorize by flipping it out and writing the triangle, can I show you guys that isn't this just a square cut in half? 1/2 S squared. Right? So the area of this isosceles right triangle is just 1/2 S squared. Well, that makes my life easier, because for us to find the volumes here, 0 to 4 of our area times a little bit of dx to give us our width, it's integral from 0 to 4 of 1/2 S squared dx, where 1/2 goes in the front. So we have our setup for what our volume would be for an isosceles right triangle with the leg on the base. And this would give us our volume. Now, over here on the right, we drew it already here. Now, you could do this and you could hate your life for it. But I have a trick, very similar to what we did over here. If I draw a isosceles right triangle on the bottom, and then I start layering them next to each other, S, 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 S. Doesn't have 45 and 45, don't they form a right angle? 45, 45. Right? So hopefully you can notice that this is actually a square. But how much area is my triangle versus a square? It's only, area here is 1/4 S squared. That is the area when we have our hypotenuse sitting on the base. If you don't like yourself and you actually want to come up, okay, so if we call this, here's another way of looking at it, if you really want to go for it. If we call this S, this is 45, This is 45. And we cut it up to try to find the height. This is 1/2 s. This is 1/2 s. Right? Because of the same 45, 45. To find the area of this is 1/2 s times 1/2 s, which is 1/4 s squared. So geometry still rules. But I think just dividing by 4 makes it easier on us. So how would we write this volume equation? Oh my goodness. It's still the integral from 0 to 4 of area times a little bit of width. That gives us our thickness to give us our volume. And hopefully you guys aren't tired of this yet. But 0 to 4 of 1/4 s squared dx, where the 1/4 goes in the front. 0 to 4 s squared dx. All right. We did it.
Mr. Ko.
Give me one sec. All right, so let's do an example of how this would work out. So let's say I give you a problem. The graph is y is equal to x squared over 2. Yeah, that looks good. X squared over 2 minus 3x minus 1/2. And we're bounded by y is equal to 3. And the graph is going to look something like some key points here. We have 1, 2, 3. And we're going down to 1, 2, 3, 4, 5 with parabola down here. We're going to go 3, 4, 5, 6, 7 on the right. And we're going up to 3, 1, 2, 3. And going to the left. -1 and 3. Okay, so we have this parabola. And we're going to block off right here. This shape looks kind of terrible. And this is what we're dealing with. Okay, so you guys can visually see that. Now, one thing now is asking, what type of volume do you guys want to build out of this? Okay, what type of cross-section you want to use? Do you want to use a semicircle, a rectangle, a square, a triangle? I don't know, whatever you want. And the problem is, the idea is that it's all built the same way. You just tell me the shape, and then we'll just look up on a list, or you can memorize a list. But let's start off with the easy one. Let's say a square. All right, so we figure out where this shape starts. It starts here at -1. It goes all the way up to 7 here. Yeah, 7, okay? All right, let's go -1 to 7. This is -1 here. -1 comma 3. And this is 7 comma 3. So we built squares. Let's go build a square. All right, we have an equation for squares. It's the integral of s squared dx. That's our volume. Okay, where are we starting? Where are we ending? We are starting at -1. We're ending at 7. What is s? S is the value from upper to lower. That's the length of your one side. How do we find the length of the one side? It's just, we can call this y1 and y2. It's y2 in this case minus y1. Why? Because y2 is my upper boundary 3. That's 3. And the parabola y1 is x squared over 2 minus 3x minus 1/2. And you are pretty much done. If you want to write it out, it's going to be integral from -1 to 7. And we're going to do a squared of 3 minus parentheses x squared over 2 minus 3x minus 1/2. And that is the setup. And this is the area, right? Because we squared it, times a little bit of width to give us volume. And the integral will add up every slice from -1 to 7. Because we're adding volumes. What if we say, hey, Mr. Ko, I want to write this as a, let's use a semicircle. To remind you, a semicircle looks like this, where that's S, right? The full length, if we draw it out, draw a messy version of it. A semicircle would look like that, like a little bulb. Sorry, it looks terrible. I'm just trying to get this out there. To remind yourself, in case you forget the formula, draw it as a cross section. And that's just, okay, if this whole thing is S, it's 1/2 pi r squared. It's half a circle, right? Applying this, it's half a circle. Okay, I can do half a circle. The r here is half of S. 1/2 pi 1/2 S squared. This leads me to 1/8, or pi over 8 S squared. Okay, so to write our volume equation, it's the integral from -1 to 7 of pi over 8 S squared dx. Is it always going to be pi over 8? Yeah, if we consider S squared my full length. So it's pi over 8, integral from -1 to 7 of S. Now the part for S, we wrote it before, is S minus x squared over 2 minus 3x minus 1/2 squared. And then dx. What if I want to make equilateral triangles? All right, equilateral triangles. It's
Oh wait, only the equation squared?
only the s is squared. Yeah.
Okay.
Only the s is squared. Oh, sorry. I erased, wrong. That should be on top.
Oh,
Okay. Thank you. Sorry, I was trying to squeeze it in there. I squeezed it in the wrong place. Thank you for catching that. How does this change? Okay, I'm getting tired of writing this. Okay, I mean honestly, I'm just writing negative. I'm gonna just write this in a way. All right, so call this crap is equal to the integral from -1 to 7 of 3 minus x over 2 squared minus 3x minus 1/2. Okay, that's labeled crap. Okay, so if I want to do a circle, if I want to do an equilateral triangle, I can't spell that. If I want to do a isosceles triangle with leg or hypotenuse. All right, I'm going to do all these equations with crap. Circle is pi r squared, which is, for us, S was r over 2. If you're not sure about that, draw the picture, cut it. That's S. So to find area here, area is pi r. Whoops, sorry, I spun that around. I'm doing too fast. S over 2. S over 2 squared, pi r squared. Rewriting it, this is pi over 4 s squared. Guess what? The integral of pi over 4 s squared dx from -1 to 7 is just pi over 4 times crap. What if I want equilateral triangle? We said this was square root of 3 over 4. If you forget, draw it out. This is s. This is 1/2 s. Square root of 3 over 2s. 1/2 base times height. 1/2 base times height is square root of 3 over 4s squared. The reason why I'm really just reformulating the questions, the theorems for you in case you forget. All right, since we see this s squared here, we know it's going to be square root of 3 over 4 integral. Whoops, that's just right crap. Because it's the same formula over and over and over again. The only thing that changes is that front constant. Let's do the legs. If the leg is on, that's my s. So to find the area, that's going to be s, 1/2 s squared. So it's going to be 1/2 crap. To the hypotenuse might be a little harder, but if you remember, if I draw it this way, it's actually 4, 1 over 4 s squared. This is 1 over 4 crap. And hopefully you've seen crap as the pattern. But really, it's just the front coefficient changes, but s squared still stays the same, because the way we're treating this model is that s is that length from the top to the bottom. Okay. All right, that's it.